Hi, everybody. Thank you for the invitation. So first, let's take a general insight of the situation. Given Hopf algebra, and if we consider a Lie algebra action on that Hopf algebra by derivation, we can construct an action on the space of morphisms that contain our Hopf algebra coproduct given by the following formula. And thanks to this, we can construct a stabilizer Lie algebra, which is the set of elements of our algebra that annihilates elements like this. So in order to construct a stabilizer, all we have to do is to construct a Lie algebra action on our Hopf algebra by derivations. Which will be what we're going to invest on for this talk. This is mainly motivated by the fact that Enriquez and Purcell demonstrated in their paper of 2018 that the double shuffle and regularization Lie algebra attached to a finite abelian group is essentially a Lie algebra stabilizer of coalgebra. But this coalgebra has there is a Hopf algebra that is linearly isomorphic to this coalgebra, and the structure of Hopf algebra is richer. So, all of this takes place in Racinus formalism, which we will briefly recall. So we have a finite abelian group whose composition law will be denoted multiplicatively. And Racine formalism is consists of the ambient space, which is Q double bracket X, which is free non-commutative formal series over an alphabet X, which is X indexed by 0 and elements of the finite abelian group. It is equipped with the Hopf algebra structure given by the fact that letters of the alphabet are primitive for this coproduct. And it also has an action of G on the Q double bracket X that fixes X0 and that moves just like this, the X's indexed by G. But this will not be our Hopf algebra we're interested in. It will be actually Q double bracket Y, which is a free non-commutative series algebra over an alphabet Y, indexed by a pair of positive integers and elements of our group G. It is identified to a subalgebra of Q double bracket X, which is linearly generated by elements that ends with xg, so indexed by our group. And it has a Hopf algebra structures with this coproduct, which is called the harmonic coproduct, and was defined in this 2002 paper. And our Lie algebra actor will be the free Lie algebra over X, which can be seen as the Lie algebra of elements that are primitive for the product on Q double bracket X. So it is naturally equipped with the Lie algebra structure given by the product of Q double bracket X, but it is also equipped with Lie brackets given by this formula. This Lie bracket is dubbed by the community as a Hara bracket, where this S psi is the left multiplication on Q double bracket X plus D psi, which is a derivation that annihilates X0 and to XG associates. So this is the usual bracket of XG and TG of psi. So now let's construct the derivation we talked about in the introduction, but in the case where G is trivial, because this case is already known, it is done by Enriquez and Purcell again, and this derivation is D psi plus the adjoint of this quantity, which is what Racine calls the correction term of the psi, However, so it is a derivation on Q double bracket X, and in the when G is trivial, it restricts to Q double bracket Y. But in the when G is general, this no longer restricts Q to Q double bracket Y. But we keep this idea of having a superior algebra where we construct a derivation and we restrict it to Q double bracket Y. So we're just looking for the most suitable candidate. And this candidate will be the cross product algebra. So the cross product algebra is basically the tensor product of Q double bracket X with the Q group algebra of G, equipped with algebra product, which is given with respect to the action of G on Q double bracket X, and is a little reminiscent of a semi-direct product. This cross product can be identified with graded algebra VG with generators E0, E1, and elements of G, satisfying the following relations. So the multiplication of elements of G is the usual multiplication on G. The unit is the unit of G, and all elements of G commute with E0. So like I said, this isomorphism identifies the cross product with VG. And inside VG, we have something that looks like Q double bracket Y, which is WG. So WG is linearly generated by words ending by E1, and it is freely generated by elements Z and G. So exactly like Q double bracket Y. And we have a coproduct of Hope algebra here, which looks like exactly to Racine's harmonic coproduct. And even more, so like I said, it is identified by this Hope algebra isomorphism. So we have something that looks like Q double bracket Y inside this. Now, we need something that looks like the derivation deep side, and this will be there 0 defined there. So it annihilates E0 and elements of G and associate this usual bracket. So this is psi transported from Racine's formalism to the cross product formalism through beta. And this commutative diagram makes the identification between deep side and their 0. And thanks to their 0, what we're going to take is that what we're going to do is to add the adjoint of the exact same quantity we had on Racine's formalism, but transported through the cross product formalism through beta. And this time, this derivation on on BG will restrict to WG, which I remind you, it looks like Q double bracket Y. So we managed to construct the wanted derivation to have a stabilizer for the harmonic coproduct. However, if someone want to know how want to have this derivation purely on Racine's formalism, so we can use our Hope algebra isomorphism to reverse engineer to Racine's formalism. And we have a stabilizer, and this stabilizer contains the double shuffle and regularization Lie algebra. And more precisely, this derivation looks like this through the previous identification. And it is a real generalization of the G trivial case that we saw, because when we take G to be equal to 1, we had exactly the quantity that we took in the first place.
All right. I'm sorry. So, question. Yes.
I might have been confused. I thought, right, in the classical case, the DMR is equal to the stabilizer. Is it right? And here, no?
Not exactly. It is the elements of the stabilizer, but with coefficients on x0 and x1 equal to 0. There is a little confusion.
Here, what about the, you have it's included in the stabilizer? What's the relation between the DMR G stabilizer that we constructed.
So we have, thanks to Enriquez and Fouchau's work, that the DMR is the stabilizer of the coalgebra product. And in my preprint, what I showed is that this stabilizer of coalgebra coproduct is included in the stabilizer of the Hope algebra coproduct.
Mm-hmm.
So maybe just a little thing that I didn't say is that when Racine constructed his coproduct, he uses it as a coalgebra coproduct, but he also has that structure of Hope algebra coproduct. He just uses the linear space and he identifies linearly with the algebra QW. This is why, for example, his projection is denoted pi y. But there is kind of a difference because we have a much richer structure with the Hope algebra product. So there is a difference, and we chose to enlighten that difference between the coalgebra product and the Hope algebra product. So we already had the DMR to be essentially the stabilizer of the coalgebra product, and thanks to Enriquez and Racine's work. But in addition, so in the preprint, I showed that we had inclusion to the Hope algebra.
Mm-hmm. Thank you.
No more questions? All right, so let's thank Alif again. And